All right, let's talk about something that sounds, well, completely backwards. We're going to dive into how breaking a tiny electronic component is actually the secret to making it work perfectly. Yeah, you heard that right. We're talking about diodes and how their failure is what powers so much of the tech you use every day. I know, it sounds nuts. How can breaking something make it more useful? But that's the thing about semiconductor physics. Sometimes the bugs are actually features. And to really get our heads around this, we have to start at the very beginning, with the most basic building block of almost all electronics. So let's get into it. Everything, and I mean everything in modern electronics, starts with something called a p-n junction. I like to call it the semiconductor sandwich. It's the core ingredient for transistors, for LEDs, and, you guessed it, for the diodes we're focused on right now. Okay, so what is this thing? Imagine you've got a pure slab of silicon. On one side, you intentionally add impurities that create a bunch of positive charge carriers. We call these holes. That's your p-type side. On the other side, you add different impurities that give you a ton of free negative charge carriers. Those are electrons. That's your n-type side. And that magical line right down the middle where they meet, that's the p-n junction. Now this is where the real physics kicks in. As soon as you put these two sides together, those extra electrons on the n side see all those empty holes on the p side and think, hey, free real estate. They rush across to fill them up. But in doing so, they create this little no man's land right at the junction. It's a zone with no free moving charges left, and we call it the depletion region. It basically becomes a natural wall with its own little electric field that says, nope, no more crossing allowed. So we've got this built-in barrier. It's just sitting there blocking everything. Kind of useless on its own, right? But what if we could control it? What if we could tell that wall when to get smaller and when to get bigger? Well, we can, and that's called biasing. It's all about applying a little voltage from the outside. And this is what it looks like in action. You've got two scenarios here. On the left, that's forward bias. We've pushed the barrier down and now current can just zip right through. But on the right, that's reverse bias. We've actually made the wall thicker, and now nothing's getting past. It's a perfect one-way street for electrons. Okay, so how do we open the floodgates? Simple. We forward bias it. We hook up the positive end of our power source to the P side and the negative end to the N side. This gives all the positive holes and negative electrons a big push towards each other right at the junction. They basically steamroll that depletion region, shrinking it down to almost nothing. Once you give it just a little bit of a nudge, about 0.7 volts for silicon, whoosh, the current flows. And if we want to slam the door shut, we just flip the battery. That's reverse bias. Now, the positive end is pulling all the electrons away from the junction, and the negative end is pulling all the holes away in the other direction. What does that do? It makes that no man's land, that depletion wall, even wider and stronger. It's like reinforcing a dam. The result? Current is totally blocked. It's like an open switch. This graph, the VI curve, tells the whole story. See that right side? That's forward bias. We add a little voltage and bam, the current takes off like a rocket. Now look at the left side, reverse bias. It's flat, nothing, no current. It's doing its job. But what about that part way, way over on the far left? What happens if we just keep cranking up that reverse voltage? What happens when we push too hard? And this is where our story really gets interesting, because we're about to find out what happens when you push that one-way street too far. What happens when that reinforced wall finally gives way under all that pressure? There's a specific tipping point. It's called the breakdown voltage. And when you hit it, well, the dam doesn't just leak, it bursts. The floodgates fly open and a huge, sudden rush of current starts pouring through the diode backwards. Look at the curve again. It's just flat, 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 and then it just falls off a cliff. That sudden drop is the reverse breakdown region. Now, for a regular, everyday diode, this is bad news. This is usually where it fries. But what if we could control that breakdown? What if that catastrophic failure happened at the exact same voltage every single time? Well, it turns out there isn't just one way for a diode to break down. There are actually two completely different ways it can happen at the quantum level. And the one you get depends entirely on how you build the diode in the first place. Let's meet the two culprits, Zener and avalanche breakdown. So on one hand, you have avalanche breakdown, and on the other, Zener breakdown. The key thing to remember is they're for different situations. Avalanche happens in diodes with a Y junction and needs a lot of voltage to get going. Think more than 6 volts. Zener, on the other hand, is for diodes with a super thin junction, and it kicks in at much lower voltages, usually less than 5 volts. Let's start with Zener breakdown. This one's pretty wild. In these diodes, the junction is so thin that the electric field becomes insanely strong, even with just a little voltage. It gets so strong that it can just reach in and yank electrons right out of their atoms, pulling them straight through the barrier. It's like the barrier is so thin, the electrons can just tunnel through to the other side. It's a pure quantum mechanics trick. Avalanche breakdown is, well, exactly what it sounds like. It happens in those wider junctions that can handle more voltage. Imagine a single electron getting accelerated by that powerful electric field. It's moving so fast that it crashes into an atom and knocks another electron free. Now you have two. They both speed up, crash into more atoms, and knock more electrons free. Suddenly you have 4, then 8, then 16. It's a chain reaction, a literal avalanche of electrons cascading through the material, creating a massive current. Okay, so here's the payoff. That avalanche effect, it can be kind of messy and destructive. But the Zener effect, the quantum tunneling one, that is incredibly precise. It happens at a very specific voltage every time. And some brilliant engineers realized, wait a minute, we can use that. So they designed a special diode that's meant to live in this broken state. And that, my friends, is the Zener diode. Just look at its VI curve. See that breakdown region? It's a perfectly straight vertical line. So what does that mean? It means that as soon as the diode breaks down, the voltage across it gets locked in. It becomes completely stable at one precise value. We call it the Zener voltage. And it stays locked there, rock solid, no matter how much current you push through it. And that one amazing trick, that ability to hold a voltage perfectly steady, is the entire reason we embrace this failure. This is what lets a Zener diode work as a voltage regulator, keeping your power supply smooth. It's what lets it be a reference point for other, more complex circuits. And it's what lets it protect your expensive gear from sudden power surges. So think of it this way. You've got a messy, spiky, unpredictable voltage coming into your device. You put a Zener diode in its path, that diode just sits there and says, nope, I'm only letting through, say, exactly 5.1 volts, nothing more. It absorbs all the chaos and spits out a perfectly clean, stable voltage on the other side, all because it's designed to live right on that edge of a controlled breakdown. So in the end, a diode's failure isn't a failure at all. It's a feature engineered on purpose. Which kind of makes you think, doesn't it? What other little glitches or bugs in physics are out there, just waiting for someone to turn them into the next big technological breakthrough? What other mistakes have we turned into magic?